Welcome back. Functional Analysis FAV 023 Part 1 of 2 by Professor Dr.A.G. Srinivasan. 23 by Professor Dr.A.G. Srinivasan. Number 1, definition. A metric space, you know what's a metric space? A metric space is said to be compact. A metric space is said to be compact if every sequence in X has a convergent subsequence. A metric space X is said to be compact, if every sequence in X has a convergent subsequence. Now, it may not be clear to you. Let me explain a note. Now, I'm using orange colors, 1, 2, 3, etc. And each has got different colors to differentiate the concepts. So what is the compact metric space? Every sequence in X has a convergent subsequence. Now, first point is this, which I'll go to here, note. Now, sorry for that, 1 second. Yeah. Now, the note says the definition given above. What is that? The definition given above. A metric space is compact if every sequence in X has a convergent subsequence. The definition given above is actually called as sequentially compact. Please remember, the definition we have given is actually called as sequentially compact. Every sequence has a convergent subsequence. This is called sequentially compact. But in a metric space, compactness, sequentially compactness, locally compactness, and other compactness, there are many more compactness, they are all equivalent. In a metric space, whether it's compact, whether it's sequentially compact or locally compact, they are all equivalent. We will show this in the next subject on topology. So I'm using sequentially compact in this context, though I'm using the word compact. They are same in a metric space. That's a very important one. By the way, what is compact? A compact set is having a property, every open covering has a finite subcovering. Every open covering has a finite subcovering. That's a compact set definition in the general sense. But I'm not using that in this definition because all the three, the compactness, sequentially compactness, and locally compactness are equivalent in a metric space. In a metric space, they are equivalent. So because of that, I take the easiest one, which is a sequentially compactness, as a compactness itself. So when you read textbook yourself of any other textbook on functional analysis, read the definition of compactness given in that book. Because for a metric space, they are same or equivalent. For a non-metric space, they are different. Okay? So read the definition in that textbook which you are referring for understanding the functional analysis of compact spaces. But we are going to fix compactness as this definition as a metric space. So in a metric space, we say it is compact if every sequence in X has a convergent subsequence. Don't get panic. It's not yet started the real discussion on what the compact space is going to do with the metric space. Please wait. Now, note 2b. What does note 2b says? It says the subsequence we talk about in the definition. The subsequence we talk about in the definition need not be finite. Need not be finite. You know what is the reason? Every finite subsequence always converges. So if you take a sequence, suppose you take a, let me explain that to you as usual in a separate window. Suppose you take a sequence. Suppose you take a sequence xn. Let's take a sequence xn. And you take a subsequence. Suppose xn means x1, x2, x3, xn is a sequence. I will now take a subsequence, let's say x1, x5, x13, x27, something, you know. This is a finite sequence. There are 4 numbers are there. If it is a finite sequence, it's always converges. So if you take a finite subsequence, it is always convergent. But my definition says every sequence has a convergent subsequence which need not be finite. Because if you take finite, nothing to verify, everything is compact in that context. So when I say a convergent subsequence, it must be not necessarily finite. It must be actually, in fact, infinite. Then only I can talk about the convergence. It's meaningful to discuss convergence. So note A says, in a metric space, compact metric space, locally compact metric space, and equivalent sequential compact metric space are equivalent. Note 2b says that the subsequence we talked about in definition of compactness need not be finite, because every finite subsequence always converges. Now, the third point is a very important point. Listen carefully. With this point only, the next concept is going to be developed. Now take a sequence xn. What is the xn? Xn is a sequence in X. Now what I'll do is, I will take some m, a subset of X. Listen carefully. What is m? A subset of X. Now I will take a sequence xn. I will now take xn, a sequence in M, and further I assume xn converges to X. Please listen carefully. Xn is a sequence in X. That's the first point. M subset of X is a part of X. Now I've chosen another sequence xn, or maybe call yn if you want, a sequence in M such that xn converges to X. Right? Now this X may not be in M. However, we already proved that M is closed if and only if X belongs to M. So if that limit belongs to M as a subset of X, then M is closed. Or if M is closed, then limit also belongs to M. That's what we proved some time back. But in general, if it is not closed, if xn converges to X, this X is not necessarily in M. You understand what I'm telling? So if xn converges to X, I'll repeat one more time, my dear students. If xn converges to X, then in general, this X need not be in M. The reason I've taken M, not X, because if you take the original space X, the parent space X, xn converges to X, always guarantee X belongs to X. Because everything should from X only, no? X is a bigger space, X is the biggest space. So even if it converges to X, it's going to belong to X. And you know very well, every X is closed. So I'm not explaining this for a X. I'm explaining for a M. Let me explain one more time. If you take M, a subset of X, if xn converges to X, where xn is a sequence in M, then X need not be in M. That's the point we have to say. However, that's the climax. However, when I say X is compact, what is the definition? This is a very important point. Every sequence, definition of compact we have discussed, every sequence has a subsequence or as a convergent subsequence. Listen carefully. Every sequence has a convergent subsequence. Now, when you take a sequence xn in X, where X is compact, if xn belongs to X, if you take yn, what is yn? It's a subsequence of xn. Then if it is compact, what we said is yn converges to Y. But what is important is this Y is the member in X. So subsequence converges to an element of X. The subsequence limit must be in X. Okay, listen carefully. The subsequent limit, it is in X. Let me explain little differently so that you understand how this is working. What is M? A subset of X. What is X? X is compact. You now take xn, a sequence in M. A sequence in M. You take a sequence in M. If M is compact, if M is compact, it's only if M is compact, then for this sequence X belongs to M, Yn, a subsequence, a part of the sequence, converges, and that Yn converges to Y for some Y, and this Y, that's the climax, this Y belongs to M. Please remember, when I take a subset, this sequence we have taken from them need not converge. I'm not telling the sequence converges, but the subsequent converges if it is compact. If M is compact, the subsequent converges, and the converging limit must be from M. That's a very interesting point. The convergent subsequence, that limit belongs to M. That is the property of the compact set. The sequence itself, first of all, the sequence itself may not converge. Even if it converges, it may not be in M in general, unless M is closed. But what we are telling is that if M is compact, then the subsequence Xn will be having a limit, and that limit will be in M. I think it's very complicated to understand, but don't get panic. You will understand when you go for the notion. Okay. So let's talk about now here the convergence. The convention use the convergent means even the limit of the convergence is in the space. I think that's what I said. Explain to you. It's a very important point. If it is compact, the converging limit must be in M. Of course, always be in X. X is a bigger space, always there, but the subsequent converging limit will be in that space. This is very clear when I explain the D part. What the D part says? A subset M of X is said to be compact if, I'm talking definition of a compact subset. A subset M is said to be compact if M is compact as a subspace. So what is subspace? We know it's a vector space by itself, it's a metric space by itself. So if that metric space is compact, we have defined what is the metric space compactness definition here. So if the M, the subset M, is a metric space in itself and it is compact, then we say M is compact. Shall I explain one more time for this so that you don't mix up things? What is X? X is a metric space. It's a metric space. What is M? M, a subset of X, such that M also is a metric space. That's the point. M also is a metric space. As a metric space, I'm calling M a subspace because M is a subset of X and itself is a metric space. If M is compact, meaning as a metric space, M is compact, then I'm telling a subset is a compact subset. So a subset is said to be a compact subset of a metric space if M itself is a metric space and it is compact under that metric. Like every sequence converges as a convergent subsequence. As I already mentioned in the previous discussion, that if Yn is a sequence in M that need not converge, this need not converge, okay, need not converge. However, if M is compact, then for that sequence Yn, you can find in Zn a subsequence. You can find a subsequence Zn such that Zn will converge to Z. But what is important is that Z belongs to M. That is very, very important. Remember, Yn need not converge. But if M is compact, Yn will have a subsequence Zn such that Zn converges to a point Z where Z belongs to M. That is a very important notion you must understand in compact spaces. And I already told you what is a subsequence. Just for revision, I'm doing it one more. If Xn is X1, X2, X3, etc. is a sequence and this is subsequence, you take some elements of that and make a subsequence. But if it is finite, nothing to discuss because every finite subsequence is convergence. So we are going to take only an infinite subsequence of the given sequence. That is understood when I say subsequence, it is understood is always infinite because if it is finite, nothing to discuss as well, right? So come back to the point. A subset M is said to be compact If M is compact, consider it as a subspace of X. Now, the last point, every sequence in M as a convergent subsequence whose limit is an element of M. I think now it's clear what we've discussed. So we have defined what a compact metric space, though the definition is not actually the compactness in general. It is only for a metric space we've defined it, because in a metric space, the compactness, the local compactness, and even sequential compactness, they are all one and the same. So in that context, we can use this as a definition in a metric space, because sequentially compact is very easy to handle. That's the reality. So we have taken the definition of a sequential compactness as a metric space. Then we made an observation that every subsequence, the subsequence must be always infinite, because every finite sequence is always convergent. So we only take the infinite subsequence. And not only that, the convergence to a limit is also there. And we define what is a compact subset. Okay, a compact subset of a metric space is a metric space by itself, but a subset of a metric space, another metric space X. And in that metric space context of M, M is compact. That is, every convergent sequence in M as a convergent subsequence. And we also said that limit of the convergent subsequence must be in M. I'll repeat again, the sequence need not converge. The sequence need not converge. Oh, something happened once again. The sequence need not converge, but the subsequent converges to a limit, and that limit must be in M. Okay, let's take a lemma. So this is a lemma. I'm going to prove it today. To start with, equation number 3. Lemma says a compact subset. You know what is a compact sub definition of a metric space? A subset is a metric is compact if it itself is a metric space, a subspace, and it is compact. That is, every sequence in M as a convergent subsequence. If that is the case, then that M is going to be always closed and bounded. What is closed by the way? To explain, to recollect what is closed, because we are in do the close for a longer period, because only open set we discussed in the first unit in detailed manner. What is the closed set? For that, I define an open ball first. So what is an open ball? An open ball is B of x0, r is set of all y such that, I'll put d of x, y instead of x0, I put x, y, such that d of x, y less than r. This is an open ball. And what is a closed ball? A closed ball has the property that it's going to be B of x, r is equal to set of all y such that d of xy less than or equal to r. So if you equal to r, it's a closed ball. If it is less than r, it's an open ball. What is an open set? An open set, U is an open set if U contains an open ball B of x0, r. If there is an open ball contained in U, we say U is an open set. And when we say V is open, V is closed, we say V is closed if x minus V is open. So we know what is a closed set I mean. So a closed set contains a closed ball. That's what I did explain to you. A closed set contains a complement as open set and so on. Okay, let's go back to the discussion again. And it's closed. And bounded, what is bounded? As a metric space, what is bounded? You take a sequence xn is bounded in a metric space, of course, if d of xn, r is less than some n for this, okay, some b, where this b should not depends on this n. Okay, the distance between xn and r, the ball should be less than b, where this b cannot depend on this n. Or in mathematical local word, the sequence xn is less than b. If you take a discrete, if you take the modulus as a metric in a real analysis context, it is this. So both are same, you know. So with the radius r is 0 and so on. So it is bounded. So we are going to show that if x is compact, okay, then it's always closed and bounded. We'll prove this now for a few minutes. It's very easy. For this, we require two results, result A and result B. It is very easy lemma to prove it. A compact subset M of a metric space is closed and bounded. What do you mean by that? Suppose you take, let me explain that one more time. If you take a metric space X, X is a metric space. What is M? A subset of X. If M is compact, if every sequence in M has a subsequence which is not finite, because finite is always there, it is not necessarily finite, such that that subsequence converges to a limit, and that limit will belong to M. Whereas the sequence we started with need not even converge. XD is a metric space. We say a subset M of X is compact if every sequence in M has a subsequence which is not necessarily finite, okay, such that that subsequence converges to a limit, and that limit belongs to M. That's what M is compact. The lemma says if X is a metric space, if M is a subset of X and M is compact, suppose M is compact, this says M is closed and bounded. What is closed? The complement is open, and so on. What is bounded also we discussed in the previous class. So we're going to prove it now. Proof is very easy with the observation we discussed in the previous discussions. Now to do this, I recollect a result which already proved long ago in the first unit. It says if M is a subset of X and F bar the closure of M in X, then X belongs to M bar, if and only if there is a sequence Xn in M such that Xn converges to X. We proved, I think, theorem 1.47 in FAV 10 part of 1 of 2. I'm not sure about the number. Check it. So what we proved is X belongs to M bar if and only if you can always find a sequence Xn in M such that Xn will converge to that point X. That's one result we have proved. We also proved in the same result 1.47b that M is closed if and only if this X also belongs to M. So Xn converges exists, Xn converges to X also exists, and that X also belongs to M. We already proved it. And one more thing we proved, I think 1.28, if I'm not the exact number, 1.28, we proved in a metric space, any convergent sequence is always bounded. Any convergent sequence is always bounded, and the limit is unique. That is not required for me, only required the point. Every convergent sequence in a metric space must be bounded. If it is a convergent sequence in a metric space, it must be bounded. A bounded sequence need not be convergent, but a convergent sequence in a metric space is always bounded. Okay. So one result, if X belongs to M bar, we can always find an Xn, a sequence such that Xn belongs to X, Xn converges to X, sorry. And if X belongs to M, then certainly M is going to be closed. And finally, we also assume the result we proved in 1.28. Every convergent sequence is also bounded. Okay. So with this, we'll go with main lemma. What the main lemma says? A compact subset of a metric space is closed and bounded. Now, we start with the X in M bar. Very easy. Don't worry. It's very, very easy. We'll do it now. Take an X belongs to M bar. Because X belongs to M bar by 3A. What is 3? This is 3 and this is A. If X belongs to M bar, we can always find a sequence Xn which converges to X. So we find that here. So there is a sequence such that that sequence Xn converges to X. So what is Xn here? There is a sequence Xn because X belongs to M bar. There is a sequence Xn that converges to X. But you are given M is compact. We saw if there is a convergent subsequence in M. See, what is convergent subsequence? Convergent subsequence basically means it's a sequence by itself. Because what is subsequence? Subsequence is a sequence of another sequence. There's another sequence. you take a part of the sequence. So subsequence is also a sequence. So when I say it sequence is a subsequence, the sequence, if it converge, because it is compact, that limit must be in M. We have discussed some time back about that. So if M is compact from 2E, what does 2E says? 2E says every sequence in M as a convergent subsequent whose limit is M if M is compact. If M is compact, every sequence its limit will be in M. So now we know there is a sequence converges, Xn converges to X. Therefore, because M is compact, that X also belongs to M. So using 3B, what does 3B says? 3B says if X belongs to M, M is closed. M is closed if and only if that limit belongs to M. So we proved instantly it is closed. So if M is compact, we proved that M is bounded. Shall I summarize one more time? You are given M is compact. Take X belongs to M bar. If X belongs to M bar, there is a sequence Xn which converges to X. Treat this sequence Xn converges to X. Now this sequence can be viewed as a subsequence by itself, because every sequence is subsequent by itself because they are same, right? But because M is compact, this subsequence converges to a limit, and that limit must be in M as well. So if that limit belongs to M, we proved already in the previous theorems in lemmas, M is closed. So M is compact implies M is closed. How nice, isn't it? Now we are going to show that M is bounded. If M is not bounded, what is M is bound definition? We say M is bounded. Recall the definition. We gave you a definition. M is bounded if distance between Xn comma R is less than B for some B. If a modulus definition is given, you go to modulus. If a distance is given, you go for D. So D of Xn comma R less than B. But this B do not depends on this N. That's the definition of boundedness. Now I'm going to show that this M is bounded. If not, assume that M is unbounded. That means it contains a sequence Yn which is unbounded such that the distance between Yn comma B is greater than N. Because if it is less than or equal to N, then it is going to be bounded. We already saw it. Now it's greater than N for some finite element B. B is fixed. We call the radius of the ball. So if it is unbounded, we want to show actually it is bounded. If it is unbounded, this is going to happen. Now this sequence gives you a property. The distance between sequence with B is greater than N always. Therefore, this sequence cannot have a subsequence which converges because it is always greater than N. As N tends to infinity, this becomes an infinite ball. If N tends to infinity, this becomes infinite ball. An infinite ball cannot have a convergent subsequence because the ball is infinite. So as N tends to infinity, this is going to become infinity. So this cannot have a convergent subsequence. But we assume that M is compact. Because M is compact, every convergent sequence must have a subsequence. But there is no subsequence which is converging. Because this sequence is a sequence whose subsequence is not even convergent. Therefore, this cannot be compact. But we assume that M is compact in my statement. M is compact in my statement is a compact subset. Therefore, it must be bounded. So proof is hardly only a few seconds. But how to prove it requires the previous results about the limit of a compact space, a limit, and then a convergent subsequence of properties and so on. Okay. So what we proved now is a compact subset of a metric space is closed as well as bounded. What about the con? This is Professor Dr. A.G. Srinivasan. Thank you.